welcome back after your 2 week break. I hope you used the time well. I hope that you did relax and enjoy the free time. As far as we can see into the future, this is going to remain the norm. This is the way classes are going to be delivered. This is the way we're going to be engaging between now and probably the end of May. Don't think there's any chance of us going back to school for the end of May. Primary schools might be slightly different to us, but I think this is basically going to be our lot. We're going to basically be computerized communication between now and the end of May. Anyway, look, short lesson today, a very, very short lesson. It's just a kind of a fill-in before we move into the final lap, which is thermochemistry. But this is on hydrogen. And hydrogen, as we know, is the lightest element on the periodic table. Okay, hydrogen is element number 1. In the beginning, as the good book says, there was hydrogen and helium. Okay, this is from a scientific point of view, not a theological point of view. In the beginning, of course, was the Word, and the Word was God, and the Word was with God. That's the Gospel of St. John. But according to all scientists, in the beginning was hydrogen and helium. And from hydrogen and helium, everything that is came to be. Okay, so we're going to just take a look at hydrogen simply from the point of view of hydrogen being a fuel and being a relatively inexpensive fuel, being a very, very versatile fuel, being one that packs a lot of energy per gram. So we just want to take a look at it and see how feasible hydrogen is as a fuel and how it is actually manufactured for industrial use. Okay, first of all, we do know it's a diatomic element. I hope you understand what that means. A diatomic element is first and foremost a pure substance, so the atoms in an element are all identical. Okay, now we know isotopes exist, so let's just park that for a moment. So if this is a diatomic element, what it means is that it is a molecular substance in which the two atoms making up the molecule are from the same element. Okay, so you've got two hydrogens sharing one electron each in order to give both of them a temporary electronic configuration similar to helium. So therefore they satisfy each other's valency and therefore they become stable. Okay, so it's covalently bonded. Hydrogen, as we said, if you remember from when we were dealing with ways in which we can increase the octane number of a fuel. Okay, remember all those ways? We had isomerization, we had what's called catalytic cracking, and we had something that we called DHydrocyclization. Now I want you to listen to that name carefully, DHydrocyclization, because there's two parts to it. The first part is the dehydro, meaning removal of hydrogen. And the second part is cyclization, which means taking something that was in a straight chain, which is aliphatic, and joining the carbons end to end, giving you an aliphatic cyclic compound. Now it's still aliphatic, because again, if you remember back before Easter, we said aromatics are things that contain benzene. So just because we take the two terminal carbons that have lost their hydrogens and tie them end to end doesn't necessarily mean they become aromatic. They become aliphatic cyclic compounds. Okay, so dehydrocyclization is the removal of the terminal hydrogens and then the joining end to end of the terminal carbons, giving you a cyclic compound. Okay, that's what I want you to remember. So what we said here was that it involved removing hydrogen gas in order to take an alkane into a cycloalkane. All right, now I think I did say at the time that hydrogen is not a waste product. In this case here, the hydrogen that is formed by dehydrocyclization is shipped off as a fuel and it's sold. So therefore, yes, it's a byproduct in terms of wanting to get a cycloalkane, but it is also a fuel for other companies. It is packaged, it's bottled, and it's sold. So they can actually take money out of their byproduct of hydrogen. Okay, this H2 byproduct is then sold as a fuel. And it's relatively inexpensive. There's a lot of hydrogen out there, so you can buy a lot of hydrogen for little money, okay? And it packs a lot of punch per gram in terms of being an efficient fuel. It is used as a fuel today, but it was also used as a fuel during the war. Now, one of these particular times that hydrogen came to its limit was when they built the large German airships. And one of those large German airships was called the Hindenburg, okay? And those of you who have a good history head on your shoulders will know that yes, it made its journey, it had arrived in New York, and just as it was docking, because it was full of hydrogen which lifted it up into the air, as it was docking, there had been an electrical storm beforehand, thunder and lightning, and the mass to which it was to tether itself had become statically charged. Now, hydrogen gas and static charges, I think you can put the picture together yourself. But there's a video here that is the actual newsreel footage of the landing of the Hindenburg in New York and the disaster that happened. For those of you then who are more theatrical, if you go into that video there, look at the right hand side of all the other videos that are there, and there's a film made, I think it was 2014 or thereabouts, but there's a dramatization of the actual disaster which is very well detailed. Go and have a look at it, because it'll show you how rapidly hydrogen burns and the amount of energy hydrogen gives out per gram. Okay, but just to know that hydrogen was used as a fuel. It was also used in order to lift things up into the air, like huge big German airships, to bring them across the Atlantic Ocean. But when the Hindenburg disaster struck, it put an end to that kind of travel, and they had to go back to the drawing boards and look for an alternative way. Of course, helium could have been used as a noble gas, which would be far safer, probably not as and probably a little bit more dense than hydrogen gas, but still would have been able to do the job. But they didn't. They went for hydrogen, and this was the result. So you can have a look at that yourself. Okay, as a fuel, there are cars out there that use hydrogen gas in order to power the engine. Okay, now obviously it's a special type of engine. It wouldn't be the 4-stroke engine that we went through when we were dealing with petrol. It would be a modified engine, and it would burn the hydrogen, which in turn would release its energy, and then that energy would be converted through various different mechanisms to drive the wheels, drive the pistons, and make the wheels move and power the car. Okay, still used. Hydrogen is used in some cars, and it's a relatively inexpensive fuel, much less expensive than ordinary unleaded petrol would be or diesel would be, but not very widespread because of the dangers involved in transporting it and if there's a crash, etc., etc. So H2, as we said already, is manufactured industrially in one of two ways. So we can use dehydrocyclization, fine, but it's a byproduct. And if you notice when we were dealing with that, it's only the terminal hydrogens that are removed. So in terms of giving us a lot of hydrogen per reaction, it's not that efficient at giving out a lot of hydrogen gas. So we wouldn't be using dehydrocyclization as a way to produce hydrogen. We'd be using dehydrocyclization to cyclize alkanes. That's what we'd be using it for. Okay, the hydrogen and as a byproduct would be sold off, but that's not going to be its main purpose. Dehydrocyclization is to cyclize aromatic, or I should say aliphatic chains. Okay, so keep that in mind. So there's two ways in which it can be produced industrially. All right, the first way is by steam reforming, and I'll go into detail on that in a moment. But this is very efficient because one reaction can release up to 3 moles of hydrogen gas per reaction. Okay, now that's quite a lot of hydrogen gas per chemical reaction. So if you can get billions of chemical reactions occurring, you can get a lot of hydrogen gas very, very quickly. All right, and the way in which they steam reform is they burn ordinary, what we call methane gas. Now methane gas, as you know, is natural gas from the oceans or from the earth, and it's also the gas that is produced by cows. So there's a lot of methane out there that can be used. We'll talk about that in a moment. The second way that it can produce hydrogen gas is by electrolyzing water. Now you might remember, if you go back to your junior cert, when we were dealing with electrolysis of water, you might have had this demonstrated in the classroom. If not, we will get to see this when we return to class. But what they basically do is they zap a sample of water. And by zapping a sample of water, you can actually split the molecules up into hydrogen gas and oxygen gas, the very elements of which water is made of. Okay, so we can return water back into the elements that it's composed of. And what we get is we get hydrogen and we get oxygen. Now both of those gases obviously have great uses. Hydrogen as a fuel, and it has other uses we'll talk about in a few moments, but oxygen of course is the life gas. So therefore oxygen too can be sold on as a product to hospitals and to the medical field and so on. It can also be used in steel cutting. We saw that when we were dealing with ethine. If you take the correct amount of oxygen with ethine, you'll end up with oxyacetylene, and that has the ability to weld or to cut metals. Okay, so steam reforming is the first one, probably the most efficient one, and the second one we already said is the electrolysis of water, and I want to look at both of those in detail. Let's take steam reforming first of all. Steam reforming involves reacting water and methane. Methane is the first member of the alkanes. Yeah, it's CH4, 1 carbon, 4 hydrogens. Tetrahedral shape, if you can remember back to when we were doing our geometry. It has 3 little legs and one this way. Bond angle, 109.5 degrees. And it's a beautiful 3-dimensional structure. If you can't remember, go back and Google it, have a look at its structure, but it's a tetrahedral structure, beautiful molecule. But what we do is we burn it in the presence of steam. Now water, as we know, in liquid form can put out a flame. So we don't use it in its liquid form, we use it in its gaseous form or in steam form. Okay, that's why it's called steam reforming. So we react the steam and the methane gases together in the presence of a catalyst. What did I say a catalyst is? A catalyst is any substance that can alter the rate of a chemical reaction while itself remaining chemically unaltered. Okay, now don't say that it speeds up, just say it alters the rate of a chemical reaction, because that takes into consideration the fact that there are catalysts out there that will slow things down. Okay, so you take your steam, you take your methane, you react them together in the presence of a catalyst, and here's what happens. Take a look at this. One molecule of natural gas and one molecule of water can give 3 molecules of hydrogen gas. Now that's a very efficient way to make hydrogen, and in fact most of the world's hydrogen is made through steam reforming. Okay, so CH4 plus H2O, you can see how the atoms in both of those molecules reorganize themselves. Okay, and again, this equation, it obeys the law of conservation of mass. There's one carbon, there's one carbon, there's one oxygen, there's one oxygen, and there's 4 and 2 is 6, and there's 6 hydrogens there. So it is balanced. But one molecule of natural gas, one molecule of water, when reacted together in the presence of a catalyst, can give me 3 moles of hydrogen. Extremely efficient and a very, very good way to make hydrogen gas. CH4 then can come from where? Well, it can come from the decomposition of organic matter. Cows produce a huge amount of methane. So actually there are farms now that are beginning to collect the methane from their livestock, because they now realize that methane is a very, very important fuel, not only from the fact that it burns with good intensity and gives us good energy per gram, but also that you can steam reform it and get hydrogen gas. So farms and farmers are now looking at ways in which they can tap the methane that's produced by their livestock and set it off as a product in order to be used to steam reform with steam to give hydrogen gas. Okay, so CH4, methane, can come from waste organic products. Waste can be treated to form H2. We've said that already. Now, whether it's decomposing waste or whether it is the gas that comes from the animals as they basically digest the food that they have, okay, because they do flatulate quite a bit, cows, they produce quite an amount of methane. So take it from the decomposition of organic compounds, or take it from the breakdown of the digestion of the grass and whatever the cows eat in their intestines and so on. So what about the electrolysis of water? Well, the electrolysis of water is where we take an electrical charge. There we are, there's your battery. And I just want you to remember, batteries are electron pumps. And we'll talk more about this when we get into 6th year. But a battery is an electron pump. Now what a battery does is it pushes electrons in one particular direction. Okay, in this case here, the battery is pushing the electrons down here, up here, and they're gathering on this, what we would call cathode. Okay, don't worry with the detail for the moment, but all I want you to remember is this. When you electrolyze water, it means that you decompose water. Now decompose, it just means breaking down into something simpler. Okay, that's what the word decompose means. So when you have H2O, you can actually break up the H and the O and reform those atoms that you make up into H2 and O2. And the lovely thing about the decomposition of water is that when you decompose water, look at the diagram here. Notice the amount of hydrogen in relation to the amount of oxygen. The amount of hydrogen is always 2 times the amount of oxygen, because the molecule itself is H2O, and the molecule contains 2 atoms of hydrogen for 1 atom of oxygen. So therefore, when we electrically decompose water, we get the same ratio in the gases that was present in the very molecule. So again, it's a way of proving that water is a triatomic element, 2 of which are hydrogen and 1 which is oxygen. So it's a 2:1 relationship between the hydrogen and the oxygen, not only in the molecule, but in the gases as they're formed by the decomposition of water molecules. So just keep in mind for the moment, the electrolysis of water is the decomposition of water molecules into hydrogen and oxygen gas in a ratio of 2:1 in favor of hydrogen. Now, so why don't they go for electrolysis over steam reforming? And I think the answer might be perfectly obvious. This involves a huge amount of electricity. Okay, so if you're going to decompose water by electricity, it's going to take a lot of energy, and that's expensive. So therefore, it is less expensive to steam reform than it would be to electrolyze. And as well as that, you'd have to have very large electrolysis apparatus in order to produce a decent amount of hydrogen. So they don't go for it. It doesn't happen. We can demonstrate electrolysis. That's about it. 99% of the world's hydrogen comes from steam reforming when it's being sold on for industry. Okay, so just keep that in mind. So there are 2 ways to make it, but one of them is by far more preferred in industry than the other, and that's steam reforming, because it's cheaper to do. Natural gas is relatively inexpensive, Steam is easy to produce. You react it to in the presence of a catalyst, you get copious amounts of hydrogen. Here, with electrolysis, you need a source of the electricity, which is energy, which you've got to pay for. So all of a sudden you're on the back foot. You're paying to produce hydrogen, which is not good for business. So they don't go down this route here. In your junior cert, as the slide says, you already learned about splitting water up into H2 and O2 gases. And this, as we said already, is an expensive process for poorer countries. So they don't do it. Steam reforming is the way to go. Okay, so what do we use hydrogen gas for? So when we produce all this hydrogen gas by steam reforming, where does it go? What do we use it for? First of all, hydrogen is, as you can see from the diagram here, a fuel. Okay, very, very efficient fuel, and is used as a fuel. Yes, it still fuels cars, it still fuels various different bits and pieces that move. So it is a very efficient fuel, packing a lot of energy per gram. So that is probably its main thrust. Okay, after that, look at the second diagram. You have nitrogen with 3 hydrogens. Now this is ammonia. And ammonia is the basis for all fertilizers. And fertilizers, obviously, are always in need by the agricultural industry. So therefore, nitrogen and hydrogen, when they're mixed together, will give you fertilizers. So there's a huge demand for hydrogen in terms of agriculture. Okay, and the last one, you probably won't guess what that is. That's spreadable butter. Spreadable margarine, yeah, which came on track maybe about 20 years ago or so. If you were growing up when I was young, if you took the butter out of the fridge, it was as hard as the hobs of hell, and you had to scrape the damn thing to get a decent amount of butter onto your bread. And as soon as you put the butter onto the bread, it tore it up into bits. Right? It was very frustrating. And then along came this spreadable butter, spreadable margarine. You took it out from the fridge, your knife went in, it spread perfectly over. Happy days. What was the difference between the unspreadable butter and the spreadable butter? Believe it or believe it not, hydrogen. The more hydrogen that we add to butter, the more spreadable it becomes, because its melting point lowers. Okay, and if its melting point lowers, that means it's softer at lower temperatures. Now, I want to introduce 2 words here, and I want to just stick with this for a moment. Most of the oils and most of the fats that we would use to make butter pre this spreadable stuff were all unsaturated. Go back to what I told you before the Easter holidays. Unsaturated simply means they can hold more. So there's double bonds present. Okay. Now, if there's multiple bonds present, if we can open those multiple bonds, we can add on more hydrogen. And the more hydrogen we add on across the multiple bonds, the softer the butter becomes. So therefore, spreadable butter or spreadable margarine is nothing more than unsaturated molecules having hydrogen added across their multiple bonds, being turned into saturated molecules. So sometimes you may hear on television, Flora margarine, for example, is high in polyunsaturates. Okay, they've unsaturated molecules, which means if they're high in polyunsaturates, that means they can hold loads. All right, they've got many multiple bonds in there, so there's plenty of room to add hydrogen on it, leaving plenty of double and triple bonds left behind. So when we're spreadable butter, spreadable margarine, when we're using those, it's because we have added hydrogen across the double bonds or the multiple bonds that are there, and we have reduced the amount of unsaturation. Therefore, we have reduced the melting point, making the butter softer at lower temperatures. Okay, so let's take a look at this. 10% of hydrogen produced is used as a fuel, so it goes directly into a fuel. Okay, it's a very clean fuel which simply produces water. Now, if you electrolyze water and you get hydrogen and oxygen, well then surely when you bring the hydrogen and the oxygen back together again, you'll get water. Believe it or believe it not, the space shuttle, if you can remember it, big orange fuel tank in the middle, and then 2 what they called solid rocket boosters. Okay, in a lot of ways in which they got rockets to go up into space, they were dealing with solid oxygen and solid hydrogen. And what they would do is they'd bring the 2 gases down and they'd burn them. Now, the first and most important effect of burning hydrogen and oxygen is the amount of energy that's given out. There was enough energy given out in the reaction to give thrust to get this thing out of the Earth's gravitational field. But the second and important byproduct was, as the hydrogen and oxygen reacted together, water was produced. But the water was taken back into the spaceship. It filled up tanks that were present in order to give the astronauts the water they needed to survive until they got back to Earth again. So quite clever chemistry. Yeah, hydrogen and oxygen, when you burn them together, produce a lot of energy, enough energy to give thrust to get things up into the atmosphere. But secondly, when you burn the hydrogen and oxygen together, you got water, which was collected, brought back into the into the space shuttle, wherever was being sent to space at that time, put into huge big containers, giving the astronauts enough water in order to help them to survive until they returned home. So clever chemistry. Just a bit of an aside note there. So 10% is used directly in fuel. It's clean. It only produces water vapor when burned. Okay. It's used in the production of NH3, which is ammonia. And ammonia is the raw product of fertilizers. So hugely important in the agricultural industry. And lastly then, if we hydrogenate oils or fats, they turn into margarine. They turn into spreadable, softer dairy products. So that's the uses of hydrogen. That's all we've got to do in hydrogen for this. I'm going to leave it there. Short class today because your first class back after 2 weeks. I don't want to tax you. But tomorrow we're going to move into thermochemistry. Thermochemistry is an extremely important part. It's the last part of our course for this year. I will take my time with it. There's a lot of definitions to learn, but I want you to go over the hydrogen, take a look at it, make sure you understand it. If you've got questions on it or you need further clarification, you can drop me an email.